All right, welcome. So this is week 2, lecture 2. We're talking about regression, and this is the second week that we're talking about regression, so this is regression 2. Now, on Wednesday, I finished with the algorithm you see on the screen, or at a very high level, an algorithm. So what we have here, just to recap, is using linear regression to illustrate the idea of learning a minimizer for a loss function iteratively. And the technique is gradient descent. Now, I just want to say something again that I said before. The linear regression solution does not need gradient descent, all right? In the first week, we derived an exact solution for the minimizer of that loss function. In the case of linear regression, we're using mean squared error. We derived that. Actually, we only derived it for univariate linear regression. But at the end, I showed you the more general version for multivariate linear regression, which was that formula in terms of the matrix version of the data, the weights, and the Y prediction. So basically, in the weights, you can exactly derive a solution for the minimizer given the data and the labels. So to make it clear, we don't actually need gradient descent to solve linear regression. We're just using it to illustrate the idea. And the algorithm setup is therefore very straightforward because we actually already have a solution for the derivative. Or at least I just told you that on Wednesday because we didn't actually really have the time to do the derivation. So what I thought I should start with today is just make clear the connections between the exact solution and this gradient descent solution. Because in general, there's, for a problem where you actually require gradient descent, so there is no exact solution, or the exact solution would be too complicated to derive or implement, then the kind of work that is done in deriving the gradient would need to be done for that different setting. So just to be clear, we're just using linear regression as an illustration of how the gradient descent algorithm works in the case that we know what we actually want. Okay, so let me take first part of the lecture today to try and go through this derivation with you. I won't go into absolutely all of the steps, partly for time reasons, partly also I want you to sort of be able to work through this kind of stuff by yourself. And there's quite a few problems in the Tucson labs for this week and further through the course that have a similar flavor to this kind of derivation. So this is kind of like, you need to know this kind of thing, not exactly this thing, although it's helpful if you do know this thing, but this kind of thing. So what we need, and I'm not sure how long this is going to take, so just bear with me. What we need is to derive, or we need a derivation of, can't write today, it's been a long week, the derivation of the gradient There we go. For linear regression, I'll just write LR. By gradient descent, I'll just write GD. Yeah, so that was the algorithm. I think we wrote that for the algorithm. So let's see what we have to start with. Well, we start with the loss function. Now, in the previous lecture, we talked about norms and how they're a very compact representation for various things. And one of those things is the loss function. So let's say a loss function is curly L for loss of, let's use weight, W for weights. So these are the parameters. Variously, I've called them theta or beta or B. You know, these are just the weights. Now, if I write this, someone tell me how to read that. What is it that we're doing here? Just in terms of what we said last time and in terms of norms and error, what is going on in this expression? Does this relate to anything you've seen before? Sorry, speak up. Sorry, I just can't hear. It's a big room. I think you're on the right track. I heard squared. Squared Euclidean norm, is that what you said? Sorry, I just can't hear. Squared Euclidean norm, yeah. Yeah, exactly right. So remember, if we don't see the 2 here in the subscript, we think it's a 2 norm, right? Because that's just that's by far the most common. And then we're squaring it, okay? So the 2 norm, what is that doing? Well, it's, okay, someone else, tell me what's going on. Thank you, that was a good answer. What's going on in the middle here? Why is this the loss function that we want? It's the residual. Yeah, it's the residual that we defined before, because y is the label set, right? It's a vector. What's the dimension of y? What kind of vector is it? What shape of vector is it? It's an n vector, right? So we have n instances, x rows in X, matrix X, and for every one of those we have a y, right? And I've already told you something about X, but what is the dimensionality of X? By the end of this course, I want you to be bang, bang, bang. It's just whatever. Well, I've already told you there are n rows. So it's an n by what matrix? P or P plus 1, exactly. Thank you. And what about W? Huh? Yeah, P vector, yeah. P plus 1. Yeah, okay, so remember, sometimes we need P plus 1 because we want to think about the offset, or I'm actually going to talk a bit about that later. If you don't see it, just assume P, and we've got, that's actually the number of columns plus 1. So it's nearly always P plus 1, and sometimes we just say P because we assume the plus 1 is there. Okay, please just get this sort of under your, it's like, it's just going to fall out, right? This is so common in machine learning setups that you'll read papers and you'll think, oh yeah, it's an n by p matrix, and that's the squared Euclidean norm. Okay, sorry for kind of belaboring that if you already know it, but you just need to get used to it, right? And the more you do it, the more you will get used to it. Okay, now someone said that what this really is the residual. So we could write this like this, where, I'll just make it clear. R is the residual. And just to be 100% clear, that we can map this onto what we saw before. Again, some of you may think I'm wasting your time because this is redundant, but just to make it absolutely clear what's going on, the sort of expanding this out into the sum form, we have all the yi's, and then we have w transpose xi. Now, this is squared. Okay, so now let's just check that we're 100% clear, because when you're programming this, nearly always the thing that you have to get right, maybe even the only thing you have to get right, is the shape of your, you know, if you're working in Python, NumPy, or even PyTorch, or whatever you're using, as long as you get the shape of your matrices and vectors okay, and you know what's going on, you're probably going to be fine. I mean, other things can happen, but the number one source of sort of things not working is usually that. So this is a scalar, right? So we have n of them. This is, what's xi? What's the dimensionality of xi? What is it? Is it a scalar? Is it a vector? Is it a what? What is xi? Yeah, row or column, doesn't really matter, but yeah, in this case, let's think of it as a column vector, and what's the dimensionality of it? P? Yeah, it's a P vector, right? And what's W? It's also P, right? So W is a vector of weights, and xi is think of it as a column vector. Well, they're both actually column vectors, but we transpose the W. Okay, so it's like a row of weight values, and that's the same for all of the examples. And then xi is your column, and it's just a row in the data, right? So just get used to this idea of, you know, sometimes we need to think of data in rows. We can also sometimes think of data in columns. It depends what we're doing. As long as we keep the shape, the dimensionality okay in our heads, we can, you know, do the working out of the problems, and we can implement the code, and it should all be fine, right? That's why I'm kind of spending a lot of time on this, because if you're not familiar with this, it might look a bit weird, but as soon as you get familiar with it, it's like, oh yeah, totally fine. W transpose X, I know what that means. Sorry, W transpose Xi, I know what that means, right? So, well, what is W transpose Xi if you actually did the operation? Does anyone know how to do that in Python? That operation? Yeah, exactly. Yeah. But what is it? So what do you get out of that? A scalar. Yeah, exactly. And what is yi? Scalar. So everything's well defined, right? So you've got your various matrices and vectors, plug them all in at the end, it should all work, okay? But if you're not quite sure, then sometimes things can go wrong, and you don't want that. So yeah, so at the end of this, we're just going to get the errors between what the model is. Our model, remember, is defined by W. Those are the parameters, and we're just taking, for every example in our data set, our training data, subtract the actual value from the predicted value, W transpose Xi. Is that the same as Yi? In general, not. Find the difference, square it, sum up, okay? So that's our error. And all these ways of writing it are exactly the same. So here's another way of writing it. So y is now a vector again. X, W, transpose, the same thing. Is this okay? If so, why? Is it okay? Yeah, because this is like, it's like this, right? Or it's like this, maybe easier to think of it like this, we're just kind of like expanding the square, all right? Just expanding the square. So if you're not sure, again, just think this is where we started from way back in week 1. So you should be clear that this thing is the same as this thing here. And you can expand that out if you're not sure. Like you can expand this square here to get something and then check that in the matrix form it's like this. Okay, so we can actually, well, I'm not going to go through the whole thing because that would take too long, but we can actually get to the point that when we expand that square, if I can make sure I write this correctly. So expanding that square will give us W transpose Y minus Y. And believe me, by the end of this course, you'll be just doing this like you were waking up in the morning. Although I have to write it down because there's too many things to remember. Okay, and then I'm missing one final term. Well, actually, before I write that final term, can everyone see where this comes from? Yeah, because we're expanding that square, right? So we have to have that. Now this thing here, right? It should be clear that we're going to get that. That's okay. This thing here is essentially coming from this and this. Now I'll say a little bit more about that in a second. And then we've got obviously this and this. We need to multiply these together. Now if you're not sort of too sure about that, you might want to work that through. Let me just try quickly to go through. I'll just make a little, I might change colors. Okay, so I'll just put it in a little box because I don't want to bother with signs and things yet. So let's see. So we've got xw, right? And we have xw. But we need to be a bit careful because we've got some transposes going on. Okay, so let's just write this. Again, I'm not totally concerned with signs and things like that yet. So we've got this term, and let's just keep with this term here. Okay, so we need those two terms. Well, actually, let me start to put in some signs. This term here, and I might put in the minus here, right? So eventually we're going to be multiplying two negatives together. Now there is a rule. If you know, you know. If you don't, look it up or check with your tutor. This thing here, xw transpose, we can write as w transpose x transpose. So this thing is also now minus. And then the same thing comes down here. Right, so at the end of that, what are we going to have? Well, we have two negatives, so it's going to be a positive. And we can just multiply these things together. So w transpose x w. Now, what I suggest you do is, if you haven't seen this before, or if you have, you're fine. If you haven't, just kind of go through it yourself, make sure it makes sense, check the dimensionality. Hopefully I haven't screwed it up and all the dimensions fit, because you've got this multiplication, right? So now, there's actually one other thing that we can do. So if we look at these two, these two. Now normally if you expand a square like this, you can just usually get two things that are essentially the same. But when we look at this, we might think, okay, well we've got a y transpose xw, and we've got a w transpose x transpose y. So we have the same components, but they're not exactly in the same order. So you might be wondering, oh, how can I combine those? Well, we can use the same kind of rule on transposes of products to do the following. I'll just do it in red as well to make clear that this is a bit of working. And if I don't get it wrong, we can write this. Y transpose X, sorry, that's transpose X W transpose. Now the claim is, if I transpose this thing, right, so this thing here, the claim is if I transpose that, that's going to be equal. And there's a reason for doing the transpose, but before we do that, why is that? Is that justified? Does anyone know? It's a scalar number. Okay, good. So you kind of know this stuff already. So now tell me why it's a scalar number. You find it's one by one. So excellent. So his answer was, if you work through the dimensionalities of the products, you're going to end up with a one by one matrix, which is a scalar. And you can transpose a scalar and it still be itself, right? So if I transpose 6, it's still going to be 6. Right, so I'm not going to go through it, but if you're not sure, just go through this, right? So what have I got here? I've got a p vector, I've got an n by p matrix, and I've got an n vector, or is transpose, but yeah, same thing. Okay, but what you're going to end up with is just a number, right? And if you're not sure, just work through that. Anyway, so I can do this, is the point. And then I apply the same rule that I did before, because I'm inside, I'm taking a transpose, so I can write it, but I just check my, yeah. So what do I want, what do I need? Okay, this is what I need. W transpose X transpose Y. Leave that in a bracket. Okay, so that was the same rule that we applied over here. So we made two observations, or we made one observation, and then we applied the same rule. So the observation was, this is a scalar, so you can write the transpose, and then we applied the transpose rule, which is the same rule that we applied to go from here to here. Now, if we look at this and this, we can do the usual thing we do with expanding a quadratic. We just sum those two terms, and what we're going to end up with is this. Okay, so it's Y transpose Y minus 2 W transpose X transpose Y, right? Those are the two terms that we pull together. And then we have the product at the end that we got, which is W transpose X transpose X W. Okay, so this gives us an expression. This gives us an expression for the loss function in matrix vector terms. Now, That's great, but we need, what do we need to do? Sorry, is that a question? No? Okay, that's all right. I thought you were raising a hand. That's an expression for the loss function. What do we now need to do? Well, we're trying to find what? We're trying to find an expression for the gradient. Take the partial derivative and let's do that. Okay, let's take a new slide to do this. So we need to find the gradient. So let's just write down what we're trying to do. For some reason, it's gone all weird. Why has it gone weird? Okay. So what we need to do is to find the gradient. Well, what we're trying to do is find an expression for the gradient. So we will take the derivative of the loss function. Strictly, it's the partial derivative or a vector of the partial derivatives, but this is just to remind us what we're doing. Okay. So let's just rewrite the loss function. So it's on the previous page, but we'll just write it again so we're clear. So the thing we got was y transpose y minus 2 w transpose x transpose y, w transpose x transpose y, then this thing here, w transpose x transpose x, w. So we need to find the gradient. So so here's a bit of notation. Some of you may have seen this before. The gradient is sometimes written like this. So L is a function of W, and you want to take the partial, that says find the gradient of that function, and as you know, that means finding the partial derivatives of this function. And it's going to be a vector of those, but we're working in matrix vector form. Now, let's see. Well, who can tell me, there's a simple thing that we can do just to get started. The first term in this loss function, what's it going to be after we take the partial derivative with respect to W? Y transpose Y is going to be 0. It's going to be 0 because there's no W's. Right, let's look at the second term. So let's think about this a second. So we've got W transpose X transpose Y. Now X transpose Y, when we're doing taking the derivative with respect to W, is effectively a constant. So this thing here, we can sort of think about as a constant. Okay, so let me just write that in red, and I'll probably rub that out. So we can think of this thing as a sort of, well, we've got 2, but let's say it's W transpose some constant. And what I'm saying constant here is just constant in the context of what we're doing, right? We're just taking a partial derivative, so it's not going to be affected because we're taking the derivatives with respect to W. That's the only thing we care about. So what? Let's just imagine for a second that W is a scalar. Forget that W transpose is a vector. But if you were taking a derivative just with scalars, what would happen? You got w times a constant, you take the derivative with respect to w, what do you get? Constant, yeah, exactly. And it's the same, essentially no difference when we're dealing with vectors. So let me just rub that out, that bit of working out. So we can say what we've got is, this pen refuses to work. Okay, what we've got is 2, the w goes away, or w transpose goes away, but we keep the constant, so it's 2x transpose y. Okay, right. Now, by the way, I'm doing this here in class just because I think we need to do it. If you want to go deeper, check out Omar's video. He goes into this in just more detail, takes more time. I'm going a bit quickly. So the last thing is, and I've linked Omar's video on the course webpage. It's a great video, sound is a bit off, but you know, I'm sure, if you're not sure about anything I'm doing here, go and check that out. He's basically got absolutely everything nailed down. And if there's still something you're not confused about, you know, that will give you enough direction to do, you know, go and look it up or ask your tutor. Okay, so it turns out that we can look at this thing here. Now, what's happening here is we're doing a matrix-matrix multiplication. So x transpose x, so x is, let's go back to dimensions. The shape is n by p, p by n, because it's x transpose, times n by p. So we're going to end up with, well, what are we going to end up with? What's the shape we'll end up with? P by p. Yeah. Whoever said that, well done. Yeah, p by p. Okay, so it's going to turn out, and I'm going to skip over y, that this is a symmetric matrix. Okay, and there's a rule when we're doing this kind of differentiation that says that when we've got something like this, W transpose Q, where Q is some symmetric matrix, we don't care at the moment, this is just a bit of working, we can treat this as essentially just something in between the product of W transpose and W, or WW, right? W transpose W is like what? What's that like? If we're doing derivatives with scalars, what's the analogy? If I say to you, W transpose W, what's that like? Squaring, yeah. It's like squaring, okay, with scalars. Same idea. We're doing it with vectors, but you can think of it, again, you know, we're not doing math here, we're doing machine learning. So I'm just trying to get to the point of just enough of the math that I understand. So if I understand it, you should be able to understand it, okay? Right. Don't think that we're doing a lot of math here. This is not really math. This is just like machine learning math, which is just, we need an answer, we need to implement it. Let's find out what the gradient is, right? That's all we're doing. Okay, so we can think of this as a square. So if we differentiate a square, what do we get? We actually did this before. Yes, that's right. So it's the, so if you think of this, if you think of it like this, if you think of the fact that we're differentiating W squared, just think of it like that. We're gonna, if we differentiate it, we're gonna get 2W, right? Now, the Q is unaffected by this, so all we're gonna do is, I'm just gonna rub this out to make space. Okay, so all this working is just to satisfy ourselves that what we can do is we can write plus 2 x transpose x w, right? That's how we got that, right? So we said x transpose w is symmetric. There's a rule that says when you're doing that kind of differentiation, you can just leave it as it is. And then we said w transpose w is like a square. So we get 2w, and we're just writing it like this to keep the dimensionality straight. I mean, there's a bit more to it than that, but I think for our purposes, that suffices. Okay. And this, okay, sorry, this is taking a bit longer than I thought, but let's see. This is if you look at, well, actually, let me go back. If you look at this, this is where this thing came from, right? So I just wrote it down last time, but that's what we've done. We've now derived that, okay? So there should be no mystery about where that comes from. And then this this form is what we used in the gradient descent learning algorithm. Okay? Does everyone see what we've done here? What we've managed to do? Are there any questions about what we managed to do? Or is anyone like kind of totally mystified? Sorry? Say it again? Yep. Yes, yes. Yeah, good question. So the question was the differentiation, the derivative of LW is going to give us the minimizer, or we're setting it to 0 to find the minimizer. Now, there is a bit of a twist because, as I said last time, when we plug this into gradient descent, we're doing a stepwise algorithm. So we're just estimating the gradient at a particular point. And because the expression that we derived for W is this thing here, we are plugging it in, sorry, this thing here is the version, but it's just rearranged from this. We've got this W here, which is what we're trying to estimate. So this is, you might think, oh, wait a minute, he's telling us that we need to find a value for W, but he's got W in the expression. It's fine in the case that we're deriving an exact solution, which is what we did in week 1, and I'll show you the relation between these two things in a minute. But for gradient descent, in general, you can't have the exact solution, but what you have is an estimate of the current gradient, initially some random number, some random vector. Then you say, okay, where should I go? Well, if it's random, doesn't really matter. And then you look at where you've ended up with, where you're ending up with, at. You take the gradient with respect to where you're at, and I'll say more about that in later lectures. But basically, you look at the data, and you say, okay, from where I was looking at the data, the direction of the gradient is now this, and I apply the step size, and off I go again, right? So it looks like a little bit of magic, but it's just taking the expression the derivative, plugging in our current best estimate for W and saying, okay, given our current best estimate for W and the data, where should I go next? And then you take a little step or a large step, depending on your step size, and you go off in that direction. And because it's iterative, the idea is that if you keep doing it again and again and again, and your data is kind of okay, and your step size is kind of right, then eventually you're going to wander down the path that leads you to the minimizer. Right? So that's the key difference between deriving the exact solution and not knowing the exact solution, but saying, okay, I can find a gradient and then plug in my data, and that will tell me which way to go. All right? That's the sort of key conceptual leap that machine learning makes over the exact derivation of the linear regression normal equations. Now, so this is just an expression for the derivative, okay? Now to convince you that, and hopefully I've convinced you that this is the expression that goes into the gradient descent learning, the gradient descent learning algorithm for linear regression. Is anyone not convinced by that? You're not convinced? You are convinced. You are convinced. Okay, good. All right, so hopefully I've convinced you that we find the derivative that we put in the algorithm on Wednesday. Now, I want to convince you that this derivative is the same as the normal equation solution, the exact solution that we found in week 1. Well, I didn't actually derive it in week 1. I did it for the univariate scalar case. But so all that you need to do is to derive the, well, maybe I'll write that. To derive the, I'll just say exact solution, which is the thing that we had before last week. Well, let me turn that into a question for you guys. We said there was a 2-step process to find the minimizer analytically, the exact thing. We took the we found the derivative, and then what's the next thing we do? Set it to 0. That's right. That will be the minimizer that we said. So let's do that. So it's this thing here, which is in our gradient descent, or a version of which is in our gradient descent algorithm. So we set this to 0. I'll just write it exactly like this, but it looks a bit weird. Minus 2x transpose y plus 2x transpose x w. Okay, so we look at this. What can we do? The first thing we can do is do you remember? First thing we can do is cancel out the 2's. Okay, so I can divide through by 2. 0 divided by 2 is 0. Right, just divide everything through by 2. So I'm going to get minus, okay, I'll just write it. Minus x transpose y plus x transpose x w. And does anyone see the next step? What did we do? Well, if you remember the solution from last week, you might remember. Huh? Yes, we just changed sides and then solve for w. So let me write it like this. X transpose x w equals, I've kind of switched it around, right? So I'm just going to write it like this. Just change sides. But we want an expression for w. So what do? Yeah, right. So if this was just scalar stuff, we just divide, right? But it's all this matrix stuff, so the matrix division isn't exactly defined. Sorry. Matrix division is not defined in the same way as we do with scalars, but there's a corresponding idea, which again, I'm going to avoid dealing with any of the math, and I'm just going to say it's X transpose X W inverse. That's kind of like the analogy of division. And then X transpose Y. And if you look, you should, if I haven't messed anything up, you should be convinced that that is the same as this exact solution that we got for linear regression. Okay, so what we've done, yeah. Come again? Thank you. Thank you. Yes, exactly. Good, I told you I was going to make a mistake. You need to keep an eye on what I'm doing. Actually, let me just, this looks a bit messy. Let me just get rid of that. Get rid of that. Get rid of that. So what I should have said is it's X transpose X, X transpose X inverse, X transpose Y. Right. Okay, so what we've done is really two things. We went back and finished the derivation that I just showed you at the end of week 1 for the normal equations in vector matrix form. And we've also found an expression for the gradient that we can plug in to the linear regression by gradient descent, which is this thing here. And you should be able to see that you get them by the same methods. So let's step back and see what we've done. There's a bunch more that I need to talk about in the second hour, but to summarize, what we've done is we've showed, using linear regression as an example, a way to define the optimizer. If there is an exact solution, we showed that that will work. That will give you, in this case, what's called the normal equations. And then we used linear regression, which does have an exact solution, but we use it as a sort of framework to just derive a gradient and then plug that into this gradient descent type approach. Now, why is this important? Well, it's important because nearly always you can't, well, let me turn that around. Linear regression is actually the exception to the rule. The rule is nearly always you can't have an exact solution for the minimizer. Nearly always what you have to do is take the gradient of the loss function, right, with respect to the model parameters, and then plug that into a gradient descent kind of algorithm, right? Many, many, many versions of machine learning are essentially that, right? That's essentially what they are. Even the most complicated machine learning models on Earth currently are basically that, right? There's a lot more. You can think of them, you can even think of them as the largest models around. You can even think of them as pretty much all based on this, right? This is like the smallest component of any of these massive networks that you're all using every day to, you know, whatever you use them for, right? It's exactly that. Now there's more to it because they're put together in various very clever ways, but it's basically this. So all it is really is a bit of matrix multiplication, finding gradients, moving in that direction. I mean, I'm oversimplifying vastly, but it's not incorrect to say this, right? It's not incorrect to say that essentially what's going on is this kind of approach. Any quick questions about what we've done? Was that helpful? Maybe, okay. I think you'll see if you go through the lab and the tute work, this is essentially many of those things many of the problems you work on are essentially variations of the ideas that we've done here. Okay, so let's take a break for about 10 minutes. For those on the recording, we'll be back in yeah, about 10 minutes. Thanks. See you then. Okay, we're back. So let's pick it up from where we left off. So what I have here is a little cartoon version of gradient descent, just to indicate the effect of the choice of step size or learning rate. There's a lot more to this than what I'm showing here, but it's important to remember that this iterative algorithm at every point, because we don't have an exact solution in general, we are doing an estimate and then we make an update. And remember, the gradient is modulated, the effect of the gradient is modulated or just changed by the step size or the learning rate. Now, that's important. So here's just a sort of indication of the shape of the loss function. For linear regression, by the way, I should say for the loss function that we use for linear regression, it has a particular property called convexity, which means that the loss function is effectively a sort of bowl shape, and the minimizer is at the bottom of the bowl. You won't always find that. In general, that's not the case. So that's another nice aspect of the linear regression setup. But here, I'm just showing two possible choices of step size alpha. So alpha in the red is small, and alpha in the blue is large, right? So imagine, so the idea is very, very crudely the following. If you are at a particular point theta I, so remember the loss function is a function of theta, and we're changing the values of theta, or W as we had, in response to the current step. So let's say the current step has the value theta I, and we're at that purple point on the loss function. Now obviously we don't know, when we're doing gradient descent, we don't know the shape of this function other than locally, right, at that particular point. You take the gradient, and that would be, it's not very well drawn, but that would be the green dashed line at the purple point, okay? That's the gradient. So you say, okay, and I want to move in the direction of the negative of the gradient. And all I'm showing here is the effect of, on the next step, what would happen. It's not very well drawn, but the idea is if I took a small step, I'd be more likely to end up at theta I plus 1 in red, okay? And that is clearly closer to the minimum than if I took a larger step, which would get me all the way across to that point indicated by the blue theta I plus 1. Okay, so the step size would mean either that you're kind of smoothly taking smaller steps down towards the minimum, or that you're kind of more jumping around. Okay, so the step size is going to be important. But that's a very, very simplified version of what's going on. Right, now, I want to next talk about, so we're dealing with multivariate regression, and I want to talk about what's behind the basic setup here. And here's another sort of cartoon version of what's going on. So what's going on is that in the approach that we've taken, what we're doing, and what we'll see with other algorithms later in the course, is that we're taking an approach that is justified on the basis of something called the maximum likelihood principle. Now again, if you've done any statistics, I'm really giving a very, very superficial, or, well, not superficial, but a high level take on why this matters for machine learning. And the way I think is useful to think about it is that the maximum likelihood principle is a version of a more general thing called Bayes' theorem, which is actually a very simple consequence of the definition of probability, conditional probability. Now, Bayes' theorem in the context of machine learning, we can think of it as something like the following. The whole machine learning problem is kind of like, we're given some data D, and we want to find a set of parameters theta. Right, so in fact, let's write that. So D is data on something that we're interested in. I'll just say data in quotes. It's just, you know, examples of the thing, the hidden function or whatever it might be that we're trying to learn. And then the theta is the, and again, I'll put parameters in because although we've been thinking in terms of parameters, it's not always quite as straightforward as just saying, oh, there's a vector of parameters or whatever. But you can think to a sort of big picture, first approximation. The problem of machine learning is, which is kind of like the main problem in statistics, statistical inference, they call it. Machine learning, we're just trying to learn. We're trying to find a set of parameters. So what we want to do generally is maximize this thing here. We want to say, we want to find the most probable parameters given the data. Now, actually, that's not quite what we want to do. Usually, there's a more complicated version of this. But if you accept that that's what you want to do, you want to find the best model, and one way of thinking about it is in terms of Bayes' theorem. We want to find the parameters that maximize we want to find what the parameters are that, given the data, give you the highest probability. Okay? And you can write that in terms of these things on the right-hand side. There are three terms, and they're commonly abbreviated or just thought of as the likelihood, which is written here as the probability of the data given the parameters. So this is the likelihood. Then the other thing in the numerator is this term here. And this is thought of as the prior. Okay, the prior, the likelihood. And then this thing in the denominator is, it says the probability of D. Now, it's the probability of the data, and there are different ways of getting that, but one way that's common, we won't see too much of this, but I'll just put it in by marginalization. But what I want to focus on is the numerator. So what is the numerator? It's these two things. It's the probability of the data given the parameters. We call that if you think of that as a function of, you think of theta as a set of parameters, you can think of that as a function of the data. Okay, so, and this thing is the prior. Now we're actually nearly always going to ignore the prior, but I will mention it from time to time later on. Probably not that much. What I want to focus on is this term here, the likelihood. So let's think about what this means. It means that if we try to be successful at machine learning, we're trying to find the parameters that maximize the probability of the data. Now, intuitively, what that means is that you can think of guessing parameters. You could think of a system that guesses the parameters, and you can think of maximum likelihood as finding some theta value that maximizes the parameters given the data. So why would that be a good principle? Well, if you look at this cartoon here, what I've drawn here is on the left in purple, it says data generating mechanism, brackets hidden. So what that is we assume that our data is coming from somewhere, and there's a particular mechanism which has a set of parameters theta, and that's where our data comes from. So it's like a random source. Now we can't see this, and this is supposed to be a wall, right, that we cannot see through. Right, so we never know what the real parameters are. In fact, we don't even know what the mechanism is. All we know is that we have some data, and that data goes into a machine learning system, which I've called the learner. And conceptually, what the learner has to do is hypothesize. This is supposed to be a thought bubble, right? So the learner is like an agent, a human, or I mean, it could be a human, but it's an algorithm that says, okay, I'm seeing this data, and I know that there are some hidden parameters. Let me try and predict on the basis of the likelihood principle what those parameters are. And if it's doing gradient descent, you know, it's coming up with successive approximations. I've written them here as theta hat 1, theta hat 2. This is supposed to be a process where it's kind of, it keeps guessing, maybe by gradient descent, or maybe it gets more and more data, or whatever it might be, what those parameters might be. Now, without going into the details, if the learner only sees data, the task is almost impossible. And there are actually theoretical results we'll see later in the course that explain that problem more precisely. But what is actually usually done is that there are some assumptions that are made in this process. So these assumptions are things like, and for every algorithm, they vary. Pretty much for every machine learning application, they vary. So one assumption in the context of what we've been doing would be that the target model, so for example, the target model, this thing behind the wall, the target model is of the form, you know, y equals xw, right? The linear regression. And we can also add another assumption, which I haven't got time to talk about at the moment, but we will come back to, which is that there's some error term, and we could make an assumption about the distribution on the error term, typically that it's a Gaussian or something like that. And these assumptions will vary for different kinds of algorithms, right? So they'll vary in terms of what the shape of, what kind of hidden model you're assuming, anything about the way the data has been generated. But any of those assumptions, and then we apply, and then we choose an algorithm, right? We just choose a learning algorithm, which is the learner in the cartoon. We choose the learner. And the algorithm is essentially this thing that is, you know, coming up with a process to generate parameters from its inspection of the data. But these assumptions are called, or the assumptions about this whole setup is called the inductive bias of the algorithm. Inductive bias is, in some ways, an unfortunate term, because bias we usually think of as being a negative thing. But bias, in this case, means we're ruling out the possibility that we're not dealing with a linear regression, right? So we're saying, yeah, we think the model's linear, we think the data generating mechanism is a linear thing, and therefore if we fit a linear model, it should do pretty well. May or not be correct, but we're ruling out any other possibilities, and that is what allows us to do learning, right? So we might make a set of assumptions. We might say, oh no, it's definitely not linear, definitely not. It's much more complicated, so we're going to need a much more complicated model. So we're going to have a different architecture, we're going to have different set of parameters, and therefore we need a different learning algorithm, right? And for the same kind of architecture, we could have different learning algorithms, right? Because they have different, you can have different ways of learning the parameters of the same algorithm. In fact, you might make an assumption about what the parameters are altogether. Okay, now just a quick note about this word bias. So bias in machine learning is a very overloaded term. It could mean what is a very important thing in ethics and ethics of AI and machine learning, which is bias where in applications data has been collected in a biased way, and therefore if you train something on it and you use the model, that can result in a bias. And that's important because there can be legal and ethical issues that arise from doing that. I won't get into that. There's an example here for facial recognition. The second, I would suggest, important use of the term bias in machine learning is inductive bias, which is exactly what I've just been talking about, right? An assumption about what you're trying to learn that allows you to make progress by choosing a particular model type and therefore a learning algorithm. So that, I would say, is a positive kind of bias. There's a third type of bias, which is a term that comes from statistics that I'm going to talk about shortly, which is a form of systematic error in estimation. There's a fourth kind of bias, which is sometimes, if we just think in the context of linear regression, we have y hat equals bx plus a, and a is sometimes referred to as the bias term, particularly in neural networks. But it just means the intercept or the offset. For linear regression, we can remove that by just setting things to 0, as we said. Okay, so that's the maximum likelihood principle and why we need inductive bias. Right, now I need to go quite quickly, so I think I will just need to switch back and log in again. Any questions about the maximum likelihood principle? No? Okay, good. Right. So now I have a few topics that I'm going to go quite quickly through, and what I'm doing here is just kind of wrapping up with a few things that I think are important to take away about sometimes machine learning in general, and sometimes specifically about linear regression. So the first one is regularization. So regularization comes up a lot. It is a general method to avoid overfitting. We haven't really defined what overfitting is yet, but it's essentially the error that is caused by lack of generalization. I think I mentioned something about this in week 1. We'll come back to it. Regularization is a class or a category of things that you do in machine learning algorithms to improve generalization. And the regularization part generally refers to making the model, which is for us in linear regression, a set of parameters, more quote-unquote regular. Essentially, it means don't make the parameters, most methods of regularization mean don't make the parameters too large with respect to the data. So imagine we have multivariate regression, and we're trying to make an estimate. Again, I'm using theta. So let's say we're using MSE as the loss function. So the loss function, so we're back to theta. So f theta is our model. We plug in xi. This is just the general form that we saw already. So that doesn't say, all that says is, I want to minimize error, right? Minimize error, minimize error, minimize error, right? That's the maximum likelihood principle being applied where you can actually show, particularly for linear regression, you can actually show that if you minimize the error, that maximizes the likelihood function, the probability of the data given theta, right? That is actually what happens. You can actually demonstrate, I don't have time to do it here, we'll hopefully get to it in a later lecture, but applying maximum likelihood under certain assumptions means that you will get something that minimizes that error. But you may say, wait a minute, I tried to maximize likelihood or minimize MSE on my data, and it didn't do too well off the training set. Looked pretty good on the training set, but when I tried it on the validation set or a test set, it didn't look quite as good. And then you look at the model and you say, well, some of these parameter values are really high. Now, if you think about what's going on, the parameter values are used in the prediction, right? It's a combination of the values of the data and the parameter values that give you the y that you're predicting. Now, if those values are large, remember back to last time when we just had the form of the regression equation, if those values are large, what's that going to do? Well, it's going to push the value of y hat, up or down, right? The larger those values, for at least some of the components, then the larger in general y hat will be. Now, if you think about what you're trying to do with linear regression, that could mean you're pushing the line, the linear regression model, away from the data. It could be, that's what could happen. So a natural thing to do is say, well, okay, let's minimize error, but let's not try and go crazy with these weights, right? Because if my weights are too big, then I might start, fitting a really crazy line, right? My y hats are going to be, pretty crazy with respect to the actual y's in the data. That's the intuition. So you can, in the second equation, see that what's happened is that you've added a second, well, you've got the squared error, you've added a second term. And it says lambda sum, now that summation is j, and you're squaring each theta value. So what you think about that as theta is a vector of p or p plus 1 components. You take the square of each of them, you sum them up. Now what's going to happen there is that if the weights start to get really big, then that loss function doesn't look as good. So the way to think about this is that the loss, the MSE that we spent so much time optimizing with, is now modulated or controlled to some extent by this. Because this says, I want to get this as low as possible. I want to minimize the squared error. Okay? Makes sense. We've done all the work to figure out how to learn with that. But now you're saying, oh, wait a minute, not so fast. If you get very low MSE, but to do that, you need very large parameter values, that's not going to look as good, right? So I add that term, which is going to make the loss look not quite as good, right? So I want to minimize the first thing, the error term, but and as long as this is not too good, that's fine. But if this as long as this is not too big, that's fine, that's good. But if this starts to get big, the theta that I picked to minimize my error is maybe not a good theta for generalizing. So in my process, I'm going to go for another theta that maybe is not the absolute best in terms of error, but doesn't cause quite as large a penalty. Okay, so that's the idea. Any questions about this idea? Because it's a really critical idea. If you've done neural networks before, you might know about things like weight decay. It's almost the same idea. In fact, it is the same idea. Is this all clear? All right, now, it matters sometimes how you implement this penalty. So I'm showing here two examples. This is the most widely used. It's called the L2 penalty, because you can express this as an L2 norm or a 2 norm. Just check back to norms. It's also has this lambda here. Where does this lambda come from? It's called a hyperparameter, right? So it could actually be learned, but learned as part of something like gradient descent, or it could be given to you ahead of time, right? So, and this tells you how much weight you're going to put on the penalty with respect to the mean squared error. A different version of this is just to take the absolute value of the parameters. You can think about what the different effects will be here. I won't go into it. Now, we don't have time to do it, but it's a good exercise to do, and I think this, probably next week, I think part of the shoot is to do something like this. If not exactly this, I can't remember, but it's something like this. You can set up an optimization problem in terms of the loss function. So now all you're adding is this penalty term. This is the 2-norm version. And then you can apply essentially the same approach that we did to derive the thing that we did in the first hour of this lecture, but now we've got the penalty term, right? So you can add this to your gradient, and you're going to get an expression. This is again, because it's linear regression, we get an exact solution, but you could also use that in gradient descent. I don't have time to get into it, but it's just a couple more steps on the derivation that we did before. Now, the L2 version, or the 2-norm version, has this exact solution, just like the normal equations of linear regression. That's another reason why the 2-norm version is more classic, more widely used. But if you use the absolute value term, you basically end up with something called lasso, and you do not have a closed form version of that. So this is the first version of a learning algorithm, machine learning algorithm, where you cannot do the exact solution, and you have to do gradient descent or some other iterative optimization method, right? So just adding the absolute value into the penalty, the regularization penalty term, means you now have to use gradient descent, right? So this is the first example, that tiny change, just going from the 2-norm to the 1-norm, the thing that we started with at the beginning of Wednesday's lecture, means now that you have to do gradient descent. Okay? All right. Are there any questions about this regularization? Hopefully it's quite clear. Okay, now I've got a whole bunch of topics to go through, and I'll have to go through them quite quickly, but there's a lot of writing on these slides, and they're designed to be more or less readable. So I'm going to go through them quickly, but you should take the time to read through them, excuse me, read through them, and treat them as notes. So the first thing I want to mention is the bias variance trade-off, and I'll have more to say about this in a later lecture. But let's assume that something I mentioned in the context of maximum likelihood, and we haven't treated so far in our derivations because we're doing just optimization. Let's assume that you think that the model is a function of the data, f of x, plus some random noise term, epsilon. And then another assumption you can make, which I mentioned in maximum likelihood, is that the error, this epsilon, is normally distributed. So this says epsilon is distributed as a normal or Gaussian distribution with the two parameters are the mean and the standard deviation, sigma squared. The mean is 0, and the standard deviation is, excuse me, some value. Okay, so this is an extended version of the assumption we'd been making before. Actually, here we're not stating that this is a linear function. So the data generating mechanism is we have a hidden target function and then a Gaussian or normally distributed noise with zero mean. So that means every value, right, every value of the target function is generated according to f of x, and a little bit of noise, randomness, is added. So what that means is that can be above or below what f of x is telling you for y. F of x tells you some value for y, and now you add some noise. And this was the basis of the example I showed you when we derived linear regression for those scalar values for the problem of predicting weight from height. And I said, here's an example of the linear regression model given the data, right? That's how that was generated. Okay, so in the case of models like this, in particular, the classic version of this is when the loss function is mean squared error. It turns out that this error can be decomposed into what's called a bias term, or strictly speaking, a bias squared term, and a variance term. Now, we'll come back to this, but this decomposition is I'm going to have to skip over this. I'll just leave this for now. Let me get to the bias variance decomposition. Okay. What does this mean? Well, it means that for any setup where you're calculating the mean squared error, you can think of it as breaking down into two terms, and these can be derived. This decomposition can be derived. The first term, so, okay, let's read this. This is now, this decomposition is, imagine you ran your linear regression many, many times on a data set of the same size, using the same hidden target function, but the data was randomly sampled according to the data generating mechanism. So this symbol here is read expectation, and it's the expectation over all such data sets. That's this curly D here. And it turns out that you can derive this, and you'll be doing exercises like this, that the two terms are y hat minus the expected value over all of these data sets of y hat squared plus the expectation over all such data sets of y hat minus fx squared. So these two terms are this term on the, well, the second term is the bias. So this is a systematic error between the estimates that are being made and the true hidden value, the label of the data, which is f of x. But the term on the right is interesting because it doesn't involve the true value, right? It just says that this is about the change per sample of the y hat that you estimate on that sample versus the mean over all of the data sets of the y hats. So this is the variance term, and interestingly, there are things that you can do thinking about the variance term. You can also try and reduce the bias term, but the point is that you can think about these two components of error somewhat independently, and people have tried to come up with better learning algorithms in terms of MSE to address either the bias or the variance or both. Okay. Right, now second point I want to mention, the meaning of the weights. Well, we talked about this a little bit before, and we said that for a univariate regression, we've got B, so a single parameter, or vector parameters. B is the change in y that accompanies some fixed change, some unit change in x. Now, if I have multiple parameters, then we can think about each one individually as the change in y given a change in one of the parameters when you hold the others constant, right? So you change one, but you don't change the others. Okay, so this is a very useful property that is one reason why people use linear regression, because particularly if you're doing some kind of modeling, right? If you read if you read somewhere that someone's modeled something in the economy where they change one variable and they say, oh, this means that something else is going to happen, very often they're doing something like this. It may be more sophisticated, but essentially they're doing something like this. So you have a model and you say, well, what if I change this? And then you see the result in the y, and you hold everything else constant. And if your model comes from machine learning, you better be sure that you've actually modeled everything that you need to model before you start making such claims. And that area is commonly addressed under the heading of causal machine learning, which unfortunately we don't have time to cover here. Now, just on causal machine learning, often you want to do that kind of what-if reasoning, just changing one variable to being true or false, like the patient was given the drug or the patient was not given the drug. You've probably heard of things like randomized controlled trials, and essentially that's what you're trying to do. All right, so if the patient takes, given the drug, takes the drug, and then you want to see what the effect is on the outcome if they take the drug and you control for everything else, in this case age. So taking the drug, a unit change in D makes a difference of 5 units for a fixed age, right? And that could be very useful in doing this kind of modeling. Okay, that's nice. You might want to do something else. You might want to say, oh, I believe there are, so I'm getting raw data, let's say in terms of age, but I might want to model a further thing, the interaction between drug and age. So we can, what's called, do feature engineering, where we introduce a new feature. In this case, it's just the product of the two terms, the drug and the age. Okay? And very often what people want to do with linear models is this kind of thing. They want to say, well, what is the difference in the model when I'm taking the drug versus when I'm not? And you can plot it like this. So, you know, that's the use of 0, 1 variables in linear regression. And that's an important reason why linear regression is still a valid and widely used technique. Okay, so something that is not strictly speaking linear regression is when you have a y value that is 0 or 1. Okay, so if you have a y value that's 0 or 1, you can think of that as predicting an outcome given the x values of the data. Now here's a second case where you can't easily do that by defining the normal equations for linear regression. So what people usually do is what's sometimes called a generalized linear model, is they have a function of the output. Okay, and the function is called the log of the odds of y. The odds are the linear model, and the odds are a probability that y is 1, conventionally, and you express that in terms of this linear model, but now you put the linear model in the exponent, so e to this thing, just our usual linear equation, and then in the denominator it's 1 plus e to the odds. And then you now have a probabilistic model, and we're going to see more on this next time, and this is called logistic regression. Technically, it's only regression in the sense that you've got a linear model, but you do this further function. Now, another way to think about this is you're learning a linear model, like we did, a linear regression, you can think of it as, and then we're putting an additional function between the output and the thing that you want to predict. And this is, in neural network language, called an activation function. And sometimes they are, in fact, just logistic regressions. Sometimes there are other functions. But it allows us to take the same linear model kind of learning that we've done before and predict, in this case, a binary outcome, or the probability of a binary outcome, I should say more correctly. All right, so time is running down. There's just a couple more topics I wanted to talk about. Now, we had an example in week one's lecture. I showed you an actual example of where a univariate linear regression could be used, and it was predicting unit sales in terms of advertising spend. And when we looked at that model, I think there were about 200 data points. We sort of made the observation that for some of the line, it was actually reasonable. There were roughly the same number of points above the line as below the line. But we did mention that at the ends of the data distribution, which was advertising spend in thousands of dollars or something, towards the left end, it didn't look very linear, and towards the right end, it actually looked like the errors were changing. They looked to be slightly bigger in terms of the y variable, which was the sales. So there are a couple of things going on here. The first one is that for a lot of the data, it looked pretty linear. Approximately half are above and approximately half are below. Then, that's an indication that the line is a reasonably good fit. The other parts of the story, we could think that they are indicating that it's not quite linear. This is called heteroskedasticity, which is that the average size of the residuals is varying along the line. Okay, so that might tell you that you want to be careful, right? So at the extreme ends of the line, excuse me, you may say, well, that's actually no longer linear. I'm going to do something else about those. In general, to be a good fit for a linear regression, you should have this sort of normal distribution of the errors around the line, right? So this is where this assumption of a Gaussian or normal distribution with a mean of 0 and some sort of standard deviation that's hopefully not too large applies. All right. Okay, now it turns out that in many cases, like that case, the model is probably not linear, or not sufficiently linear to have that nice sort of Gaussian distribution around of the points around the line, and that they're not too far and they're not varying across the data distribution. But if that's not the case, and you start off your machine learning attack on whatever problem you have to solve with linear regression, which, as I said, is often not a bad idea, the next thing you do is try and extend the model class. Okay, so as we've been saying repeatedly, linear regression assumes this data generating distribution mechanism is linear. Although we don't know the form of the function, if we think it's linear, then on average, in expectation, that should work. But if it's not linear, then we should really extend the model class, right? So remember, right back at the beginning, I said we make an assumption about the model class, we define a loss function, and then we try and fit it. If it's nonlinear, you could still use linear modeling. Obviously, there's other algorithms that we're going to get to. You could still use linear modeling because the linear modeling assumption is about the form of the linear function in terms of the parameters that you fit, right? So if you think, well, I've got a bunch of values for my x vector in my whole x matrix, and then I've got a bunch of parameter values. And the form must be a linear model, a linear combination of those x columns, if you like, times the parameter values, the w's or the thetas. But if that is true, well, okay, let me rephrase that. If the data itself is not such that you can easily find that relationship, you can do what's called data transformation or feature engineering, and you can change the input data to a new data set where the model is linear. And that's called a linear in the parameters model, right? So the data itself, the original data, the raw data, you may not be able to find a nice low error fit to that data using a linear model. But if you transform it into a new version of the data, you can now move into a new sort of space where the variables do have a linear relation in terms of the parameters, right? So that could happen like this. To say the hidden function was really this, y hat, or y is b0 plus b1x1 plus b2x1 squared. Okay, you can now create, that's not linear, right? That's not linear in the parameters, because this is a linear function of this, this thing here, which is not linear. Sorry, this is a linear combination of this thing here. This is not linear. Okay, so you can come up with a new variable, which is actually representing this thing here, x1 squared, and you can just say, okay, x2. And you generate all the values from your data set in terms of x2, and as long as when you're doing prediction, you can also generate those values, you can now fit a polynomial relationship like this by adding new variables. Here's another example. If in fact the relationship was the product of these two exponents, so x1 is real data, x2 is real data, raise them to the power of two parameters, b1, b2, and multiply them all together. If you apply a log transform to the data, then you can fit a model of this form. And there are many, many ideas about feature engineering that people have used. You can take various transforms of the data, and if as a result, the model, you can form a nice low error fit of the model in that data space, then essentially you've done the job. Okay, now I'm running out of time. So let me just finish by pointing out that this is about model selection for features. The last point I want to fix on, again, all of these last slides are sort of written so you can just read them. The last slide I want to fix on is also related to generalization. Okay, so if the model was something like this, so we said before that the coordinates, now we're back to univariate regression just because we're drawing on the slide in 2 dimensions. So y is a function of x. If we fit a linear regression to minimize MSE as we've developed, then what we know is that the points mean of x and mean of y must lie on that line. We had a mathematical statement to that effect back last week, so check back with that if you're not sure. Now, what does that mean, though, in terms of points that are further away from the mean? Well, as is sort of diagrammed here, you start to become less confident about values that are a long way away from the mean. Okay, so this is guaranteed to be on the line, but the further away you get in X, then the less reliable are your predictions about Y. Now, we're not going to quantify that here, but intuitively, if you're not too far from the mean, then because it's a linear model, the difference in Y should not change that much, right? Y, the mean of Y is on the line for mean of X. If you move away from the mean of X, then the mean of Y, the value of Y should not change too much from the mean. But the gradient, the slope of the line should change. But the further away you move from that mean, the less likely it is to be true. Okay, so here are different models that are a consequence, and then the further away you get, the less confident you can be. So further away from the mean value, you need to be a bit careful. And the second thing to be aware of is something that we did mention at the start, which is that we have this inductive hypothesis that this will generalize well as long as pretty much the same data conditions hold that applied to your training data. And if that's not the case, then generalization is more difficult. All right, so just to finish, we've got to the end of 2 weeks on linear regression. We've done some general statements about machine learning. We've derived some particular techniques, including the most recent one, which is gradient descent. These techniques, you'll see, come back in later versions of what we look at in machine learning. And these ideas about linear models will definitely come back. And there are many other methods. Some of them are shown here. Local models, you can do regression. Tree structured and ensemble type models you can think of in terms of linear models, and certainly neural networks you can as well. Okay, time's up. Thanks for coming. See you next time. Have a great weekend.